Welcome to question session 5. So in last question session we have discussed our second law of thermodynamics and some part of our entropy. In question session 5 we will be discussing the remaining questions of entropy, and after that we will also try to cover the questions on exergy. Okay, so let's start with the question number 9. Two copper blocks, each of mass m, are having specific heat C, are used as a heat source and sink to derive a reversible heat engine. Okay, let's say there are two blocks. Okay, this one is temperature Th, this one is temperature Tl. Okay, and both are copper blocks having mass m and heat capacity C, mass and C. Okay, and there is engine placed in between them. Okay, let's say this is engine. Okay, the engine keeps producing work till two blocks attains the same temperature. Okay, the amount of work that can be produced. So what we can do from here is that although we don't know the direct formula for the work done, we will calculate it completely here. Okay, so let's say that del q amount of heat is transferred from this surface to the next. Okay, or we can directly say that q1 amount of heat is supplied from higher temperature block to the engine, and q2 is ejected to the low temperature copper block. Okay, now we can say that for a reversible heat engine, the engine total work required to the engine, given that this is a reversible heat engine. Okay, so here we will considering the reversible heat engine, we can say that delta S of the universe is equal to 0. Okay, now what we can do, we can write the delta S for system. Let's say this is 1, this is 2. Okay, so delta S for 1 plus delta S for 2 plus delta S for engine should be equal to 0. Okay, now delta S for a solid block, we can write change in entropy is equal to mc ln. Let's say it attains the final temperature of T, and here it also attains the final temperature of T. Okay, mc ln T by Th plus mc ln T by TL. Okay, plus since the cycle engine is reversible, so change in entropy will be 0, equal to 0. Okay, from here we can, after solving this, we can obtain our value of T. Let's say Tf. Okay, final temperature. So both of blocks will reach final temperature is equal to root of T1 or TLTH. Okay, so this is our final temperature. This is a geometric mean of the temperature of two blocks. Okay, now to obtain the work output, okay, to obtain the work output we can do it like q1 minus q2. Okay, we know that the value of q1 should be mc into, and one thing more, since we are writing q1, so you should know that this value of q1 should be like temperature mc dt. Now here what should be the value of temperature difference we should take? Okay, so we can say from here that th is greater than tf. Okay, temperature tf will reduce to tf to attain the equilibrium. Okay, so we will write mc th minus tf minus mc, here it would be tf minus tl. Okay, now from here we can write mc times of th plus tl minus 2 times of tf, and this tf can be written in form of like root tl th. Okay, now from here we can write or we can directly see the given option. This is the correct answer. Okay, now if we consider question number 10, it is mentioned that irreversibility in a thermodynamic cycle, irreversibility in a thermodynamic process is caused by. Okay, so earlier in the lecture I mentioned you about some reversible and irreversible processes. Okay, we will see all the options. Heat transfer across finite difference, this is irreversibility. Okay, so the irreversibility caused by this. Okay, let's take this point. Friction effect, yes. Unstrained expression, yes. This is also irreversibility. Mixing of two decimal pure substance, sure. So option D is correct for question. Moving to next question. Next question is a closed system with internal irreversibility undergoes the cycle process, the cyclic integration. Okay, so we know from closest inequality that integral of del q by t should be less than equal to 0. Okay, so it's always less than equal to. Okay, but it is mentioned that there is irreversibility. Okay, so for in case of irreversibility, it is always less than 0. Option D is correct. Okay. Next, question number 12. The heat engine operates between two thermal reservoir, one at 100 degrees Celsius and okay, let's do it here. So we will start question number 12. A heat engine operates between two thermal reservoirs, 100 degrees Celsius and 20 degrees Celsius. Removed from the hot reservoir. The change in entropy of the hot reservoir is okay. So change in entropy of the hot reservoir, we can say that it is like given by q by t. Okay, how much heat is removed at what temperature. Okay, so we can see that higher reservoir we like remove the heat, so since we removed it should be negative 373 upon t. T is 100 degrees Celsius, so 273 plus 100 we get is equal to -1 joule per Kelvin. Okay, option C. Moving to question number 13. So water from two branches of a pipeline at a mass flow rate of 1 kg in from each pipeline. So let's draw a simple line diagram. So let's say that this is pipe 1, this is pipe 2. Okay, and both having mass flow rate m dot is equal to 1 kg per second. Okay, here also m dot is equal to 1 kg per second. Okay, combines to form a single pipeline. The inlet stream, one inlet stream is it. Okay, so here it is given that T1 is equal to 70 degrees Celsius. It is also given that T2 is equal to 40 degrees Celsius. Okay, the mixing process can be considered to be steady state and adiabatic. Okay, so it is mentioned that it is steady state and adiabatic. The kinetic and potential energy of the engine are negligible. Specific heat of the water is given as this. The rate of entropy production in the mixing process. Okay, so let so this is m1, this is m2. Let m3 be the mass, final mass. Okay, m3 dot is final mass flow rate, and let t3 be our final temperature. Okay, so since the system is at steady state and adiabatic, so energy we can apply conservation of energy. Energy in is equal to energy out. Okay, so energy in is given by m dot 1 c t1 plus m dot 2 c t2 is equal to m dot 3 c t3. And one more thing we can write from mass conservation, m dot 3 is equal to m1 dot plus m2 dot, so we can get m3 dot is equal to 2 kg per second. Okay, now so by applying this equation I can directly obsolete the c from all the equation. Okay, now I can get here from here t3 is equal to t1 plus t2 by 2. Okay, now since we have calculated the final mass and the final temperature of the system, if we want to calculate the rate of entropy change of the water, we can write this T1 temperature as T1 is equal to, I can write it as 343 Kelvin, and similarly I can write T2 is equal to 313 Kelvin. Okay, so from it this I can calculate our value of T3 is equal to, I can find T3 as 328.1 Kelvin. Okay, sorry, this should be 328 Kelvin. Okay, 328 Kelvin. And from here since it is asked to find the rate of entropy production. Okay, so if we calculate the net, we write like, if you consider this simple system, let's say inlet from 1, outlet from 2, and the system condition is let's say the S generation is generating entropy generating inside the system. So we can write S1 plus S gen is equal to S2. So we can calculate Sgen is equal to S2 minus S1. So our delta S is basically S generation. So if we want to calculate rate of entropy generation, we have to calculate delta S of the system, which will be like, if there are two fluids, so we will calculate delta S1 plus delta S2. Okay, now for both, since both fluids are similar and have reached the temperature, same temperature after mixing, so we can write delta S1 is equal to MC ln, sorry, M1 C ln T final, that is T3 upon T1, plus M2 C ln, or here it should be M1 dot M2 dot, because this is rate of entropy generation, entropy change. Okay, ln T3 by T2. Okay, now if we substitute all the values here, so we will get M1, we have given 1 into 4.2. okay, if we multiply by ln T3 by T1, we will get value of T3 is 328. okay, and the value of T1 is our 343. Similarly, okay, now since M1 is equal to M2, we can definitely take them common. Okay, and here it will be ln of T3 square T1 T2. okay, now here by solving this, we get S generation is equal to, so if we solve all this, we will get 8.8 watt per Kelvin. Okay, so answer A is the correct here. Option A is the correct. Okay, now if you move to question number 14, it is given that a metallic object cools from temperature T1 to temperature T2. The specific heat of object varies as this. Okay, the change in specific entropy of the object during the cooling process. Okay, so you know that like a small change in entropy is given by del Q by T. Okay, so we also know that this del Q can be written as mCp dt by T. Okay, now since here it is mentioned as this is heat capacity C, so specific heat, so we use capital C here. Okay, so the C value is given A plus BT square into dt divided by T is equal to ds. Now we will integrate both side. Okay, from temperature T1 to T2. From here we will get our delta S is equal to A times of ln T2 by T1 plus B times of T2 square minus T1 square divided by 2. Okay, so this will be our correct option. Okay, this one is our correct option. Okay, moving to next question. It is given that rate of change of enthalpy with respect to entropy at a constant pressure. Okay, rate of change of enthalpy, so enthalpy with respect to entropy at a constant pressure for a perfect gas. Okay, we have been asked if this value increases as T increases, decreases as T increases, is independent of T or none of the. Okay, so what we can do here, that we can dH we can write it as Cp dt by ds. Okay, at constant pressure, since pressure is constant, we can take Cp out, Cp times of dt by ds at constant pressure. Okay, now it is mentioned that at a constant pressure increases. So if we increase the value of, if we increase the temperature value, so dt will be positive and hence this term will be positive, so it increases with increases T. We can also write like it is, since it is mentioned at constant pressure, so we know that del Q at constant pressure can be written as del H Okay, now this change in this small heat can be written in terms of entropy at T times of ds, using the uh, like delta S is equal to del Q by T. Okay, so using this if we substitute this here, so we can get that del dH by ds at constant pressure, we can mention it equal to T only. Okay, so from here we can directly see that it is directly proportional to temperature. Next, on moving to next question, question number 16, it is mentioned that for any process at all, the second law that the second law requires that the entropy changes of the system is okay. So we know that for a system, del Q by del T is like we also any so we know that for any process del Q by del T is should be less than equal to 0. But here, if we talk about for any process, like it is mentioned, the second law requires that entropy change of the system. Okay, so if we talk about entropy change, so we also say that entropy of the system, okay, will be always greater than equal to 0. But we also know that in case of irreversible process, when there is a heat rejection, our change in entropy of the system may be positive, negative, or 0. Okay, so we know that it might be positive, negative, or 0. This is also only in the case of reversible. Okay, this is in case of irreversible and along with heat rejection. If there is variance of heat rejection, then the entropy change might be positive, 0, negative. And since it is here, it isn't mentioned it's talking about reversible or irreversible, we will go with option D. Now let's say that if it is mentioned that the process is reversible, so option would have been A. Okay, now moving to question number 17, it is mentioned that for an ideal gas, the slope of constant pressure line on TH diagram at a state T node. Okay, so from TDS equation we know that TDS is equal to H minus VdP. Okay, now since the process is constant, we can directly write it as 0, and we can write TDS is equal to, for H we can write it as Cp dt. Okay, now from here we can write del T by del S at constant pressure is equal to T by Cp. Okay, so it is here what was it asked, slope of constant pressure line on TS diagram. Okay, now we can write Cp is equal to, so T upon gamma times of R gamma minus 1. Okay, so Cp is equal to gamma times of R upon gamma minus 1. Okay, so after substituting it here at temperature T is equal to T naught, we can write it as, at temperature T is equal to T naught, we can write it as gamma minus 1 divided by gamma R times of T naught. Okay, so option number A should be the correct one here. Okay, now moving to next question, question number 18, it is mentioned that a block of hot metal mass 1 kg and specific heat 1 kilojoule per kg Kelvin, initially at 600 degrees Celsius, allowed to cool down to room temperature 30 degrees Celsius, calculate the change in entropy. Okay, so simple question, we know that for a fixed mass, for a finite mass system, we can write change in entropy is equal to mc ln T2 by T1. Okay, we know that mass is 1 and specific heat is given as 1 into ln final temperatures. We know that it reaches room temperature 30 degrees Celsius, that is 273 plus 30, and initial we also know that is 273 plus 600. Okay, now if we solve this this equation, we will get our change in entropy to be minus 1.058 kilojoule per Kelvin. Okay, so option B is correct. Moving to question number 19, In an adiabatic enclosure, 1 kg mole of an ideal gas undergoes a free expansion. Okay, so this is a case for free expansion until its volume is doubled. Sure, no problem. The total energy change for the system and the surrounding is, sorry, total entropy change for the system and the surrounding is. Okay, since it's a gas and is undergoing our expansion, let's say, although it's free expansion, let's call it a change. So we can write for gas the change in entropy is written as m cv ln T2 by T1 plus mr ln, sorry, V2 by V1. Okay, this is our change in entropy equation for an ideal gas. Now here we can say, since it is case of free expansion, in case of free expansion T1 is equal to T2, so this term will be equal to 0. Okay, now from here we can write our delta S value term to be m into r. So value of m is given to be 1 kg kilomole, 1 into r is written as it is ln of V2. Now it is said that the until its volume is doubled. Okay, so this will be V2 by V1 is equal to 2. Okay, so we get a value as r ln 2. So for option 2, question 219, the answer is B. Now moving to question number 20. In question number 20, it is mentioned that the reversible engine, modified Carnot engine, is shown in the figure. Receives 100 kilojoule of heat at 500 Kelvin and 40 kilojoule at 400 Kelvin. Heat is ejected at Kelvin. The work output is okay. So from here we know that. So first, what we have to do, since we know the temperature, so the Q is somehow related to the change. Like we can write Q is equal to T into delta S. Okay. Now if we like, I will name the process 1 2 3 4 5 6. Okay, so the cycle is 1 2 3 4 5 6 1, and since we know that heat from Q to 1 to 2 is given at 100 kilojoule, and its value will be equal to like T delta S. So T is 500 Kelvin into delta S from 1 to 2. Okay, so from here we can find delta S from 1 to 2 is equal to 0.2. Okay, 100 divided by 500 is equal to 0.2. Now moving to next part, for similarly for we can calculate delta S for process T3 to 4 will be heat supplied, that is 40 divided by at what temperature it is applied. So answer will be 0.01. Okay, so in the 0.01 it would be 0.1. Okay, now if we like, we know that the heat is ejected at 300 Kelvin. Okay, so heat, we know the heat supplied is equal to 100 plus 40 is equal to 140 kilojoule. Now we can calculate heat rejected is equal to T times of delta S 5 to 6, and delta S 5 to 6 value will be equal to delta. So this value of delta S will be equal to this value plus this value. Okay, so delta S 5 to 6 is equal to T into delta S of 1 to 2 plus delta S of 3 to 4. Okay, so substituting values, we can get this value is to be 0.3, and on dividing multiplying it with 300, we can get it as 90 kilojoule. Okay, so we can calculate our work output is equal to Qs minus Qr according to first law of thermodynamics. Okay, and we will get the work value to be 140 minus 90 is equal to 50 kilojoule. Okay, so correct option is D. Now we will move to next question. So if we look at question number 21, it is given that an ideal gas undergoes a thermodynamic cycle which when represented on TS diagram is a circle with a maximum and minimum temperature of 600 and 300 Kelvin. Okay, so it is mentioned that for question number 21, it is mentioned that on TS diagram, let's say this is TS diagram, TS, we get a circle. Okay, now it is mentioned that the circle have the maximum temperature of 600 Kelvin and the minimum temperature of 300 Kelvin. Okay, now it is asked what is the efficiency. Okay, so this is a cycle. Okay, let's say this is a cycle. Since it is clockwise, it will be work producing. Okay, so let's consider that this is point 1 and this is our point 2. Okay, so process 1 to 2 is this half semicircle and process 2 to 1 is this second semicircle. Okay, so if we talk about heat addition to the system, we can write it as, okay, and let's say these points are A and B. Okay, so we can write QA is equal to area, and let's say this is process X, this is process Y. Okay, or we can also call them P and Q. Okay, so we can say from is the area 1P 2B A1 is the heat addition. Okay, this complete area where will be our heat addition. Okay, now if we talk about the heat rejection, this area is our heat rejection. Okay, so if we calculate this, so we can calculate, QR is equal to area 1 Q 2 B A1. Okay, so how we will calculate these values? So let's calculate them. QA is equal to, we can see that this is the area of our rectangle plus area of a semicircle. Okay, now this temperature here should be 450 Kelvin because it is in between 300 and 600 Kelvin. Okay, now we can calculate QR is equal to 450 into, let's say this is our distance. Okay, so this distance should be also, like they say that if this complete difference is 300, so this difference should also be 300. Okay, so QA 450 into 300. Okay, plus pi by 2 into pi r square by 2, 150 square. Okay, so this radius of this circle will be 150 here. Okay, so we can use it to calculate the area of QA. Okay, now similarly we can also find QR is equal to 450 into 300 minus pi by 2 into 150 square. Okay, so if we calculate these two values, let me find it here. So we get our Q addition as pi divided by 2 into 150 square plus 450 into 300. Okay, so we get the value of Q is equal to 170342.9 this kilojoule. Okay, now if we talk about our efficiency of the cycle, then cycle efficiency can be represented as work done upon Q addition, and work done is Q addition minus Q rejection upon Q addition. Okay, so this Q addition minus Q rejection, we can write it as like difference of both terms. So it would come out to be pi into 150 square, which would also be the area of the circle, divided by QA, which we have calculated. Okay, and if we calculate these both values, we can get the answer as efficiency is equal to 41.5%. Okay, so your option B is correct. Okay, now we will move to our question number 22. In question number 22, it is mentioned that increase in entropy of the system represent increase in available energy, increase in temperature, decrease in pressure, degradation of energy. Yeah, sure, it is degradation of energy. Okay. So when entropy increases, it increases basically the loss of availability we have seen in the previous lectures. Okay. So let's say that if so what happened if the same amount of heat is applied at a high temperature and a lower temperature? If we compare them at lower temperature, for to supply same amount of heat, the entropy change will be higher. But at that point, our energy will also have like degraded, and its available energy would have decreased, and the amount of unavailable energy will increase in such a process. Okay. So this is then true here, and if we talk about increase, then increase in entropy of system represent. No, not always. Like if we talk about the same amount of heat, it is if the same amount of heat is available at higher temperature, okay, then our system entropy will decrease. Okay, you can get all these like options from TH imagining TH diagram. Okay, now if you talk about C, decrease in pressure. Okay, so if we increase the pressure, if we increase the fluid pressure, let's say the air, and if we increase the pressure, then the randomness will be increasing. Okay, if we decrease the pressure, randomness will decrease. Okay, so option D is correct here. Now we moving to question number 23. It is mentioned that ideal gas heated 1 at constant volume and constant pressure from initially state 1 to which of the following diagram are shown, two processes are correct. Okay, so it is mentioned that there are two processes, uh, constant volume process, constant pressure process from initial state 1, and which are correct. Okay, so we have to draw constant pressure and constant volume process on TH diagram. So we have already done this in class. If we you draw constant pressure and constant volume, then the slope of curve for constant pressure is equal to T by Cp, and for constant volume is equal to T by Cv. Now, since Cp is greater than Cv, so our slope for constant volume is greater than that of slope for constant pressure. Okay, so this is be our, let's say, volume, constant volume, so this should be our constant pressure. So option D is correct. Moving to next question. So D option correct, as I mentioned here. Okay, now moving to next question, question number 24. It is given that a TS diagram is shown and the thermodynamics have all the processes are straight lines. The efficiency of the cycle is given by. Okay, so efficiency of any cycle is given by work done upon Q supplied. Okay, now work done is generally the area of the like curve on whether it is TS diagram or PV diagram. So we can write, let's write it differently. Okay, separately. So we can write work done is equal to half into base into height, and what is base? Okay, so all the process line efficiency. So assuming this to be, let me think for a moment. So this dimension is not mentioned here. We can use the separate method. So let's say that here heat we light it in different way. That is, work done is equal to Q addition minus Q supplied minus Q rejected upon Q supplied. Okay, now we can, from here we can mention that Q supplied will be in process from 1 to 2. Okay, and let's say the change in entropy to be delta S. Or we can we can also do it using the same approach that we previously did. So work done is equal to half into base is our delta S for the triangle, into height is th minus tc. Now if we talk about heat supplied can be written as th t into delta S. Okay, so because heat supplied is only from 1 to 2, and heat in process 1 to 2 and 1 to 3 to 1, there will be some heat rejection. Okay, so we can write efficiency is equal to work done, that is half into delta S into th minus tl upon Th into delta S. Now delta S will be, both will omit each other, and we will get the value is equal to 0.5 times of Th minus Tc or Tl, like here it is given Tc, okay, divided by Th. So option B is correct, okay. Now moving to next question, which is a match type question. So it is mentioned that first option is del P constant volume process. Okay, so we know that for constant volume process, the slope of dt by ds is T by Cv. So the answer should be 3. Constant pressure, we know that slope is T by Cp. Constant temperature process, if you take constant temperature process, then let's write Pv is equal to mRT. Okay, now if we let's say differentiate it, we will get Pdv plus Vdp is equal to nRdt. Let's say this is a constant temperature. Okay, so we get our dp by dv is equal to minus p by v. Okay, so sorry, for this it is 1 for this, and this is constant entropy process, so this is isentropic. The option will be 2. So 3412 is the correct option. 3412, option number C is the correct option. Okay. So the question number 26, it is mentioned that an ideal gas contained in a rigid tank is cooled such that T2 is less than T1 and P2 is less than P1. Okay, so both at pressure temperature is decreased. In the given TS diagram, the process path is represented by the line label A, B, C, D. Okay, we have to tell from which process we can represent the process. Okay. So if you read the question carefully, you will see that it is given that ideal gas contained in a rigid tank. Rigid tank means volume is equal to constant. Okay, so for a constant, you know that the slope of constant volume process is greater than that of slope of constant pressure. Okay, so option should be A. Okay, now moving to next question. It is also a match type. So we have to match the curves from PV diagram on TH diagram. Okay, so here we can see, we know that in PV diagram we represent, okay, we represent our our state equations by equation PV की power A is equal to 0, sorry, constant. Okay, and the K value increases in clockwise direction. Okay, so we can see from here that this process B is our constant pressure process. Okay, so since it's constant pressure, so in TH diagram it is represented by a curve, and either it will be 2 or 3, but we know that constant pressure process is having less slope than the constant volume, so option should be 3. Okay, so we can, for B we can write it as 3 most probably. If not, then it might be 2, but we will keep on to that thought. Okay, if we talk about A, process A is our constant volume process, and of course constant volume process is represented by 2, so constant A by 2, B by 3. Constant pressures, the curve C is our K is equal to 1. Okay, when the process is isothermal, and since temperature is constant, it will be represented by process 4. And if we talk about our constant process, our D process, okay, so this is the polytropic or adiabatic, PV की power gamma is equal to constant. Now here we can see that either it can be process 1 or process 5. To decide, we can see that what would happen if like we can see that the pressure of the system, so with the along the process D, the pressure is decreasing. Okay, so this is the constant pressure curve. Okay, now if the pressure decreasing, so it means that it will be like this. Okay, so correct option is 5. Okay, now let's say that here if the pressure are increasing, so the constant pressure slopes, these are constant pressure curves. Okay, V is equal to constant curves. Okay, so option V should be correct option. Now if you move to next question, so in this question number 28, so question number 28, it is given that a system is changed from given initial state to a given final state by two different processes, one reversible and other irreversible. The entropy change of the system for irreversible process is always equal to. Okay, so here it is mentioned two things. So system is changed from initial state to a final state by two different processes. Okay, one reversible and one is irreversible. We can say that the entropy change for irreversible process may be positive, negative, or zero. We know from like in case of heat reaction irreversible process, entropy change can be zero, positive, or negative, anything. And it is mentioned that how the entropy change will be in comparison to reversible. So in case in comparison it may be like greater than or maybe less than, we can't say anything. Sorry, for reversible process we know that for reversible process it is like most, we may say that maximum work producing device process or most efficient process. Okay, most efficient. So in case of reversible, delta S for reversible is always less than delta S of irreversible. So it is mentioned that the entropy change for system for irreversible process, it will be always so the entropy change for the irreversible process is always uh, greater than energy change for reversible. Okay, now moving to next question, question number 29. It is mentioned, so question number 29 mentioned cycle on PV diagram. It wants to like plot the same cycle on TS diagram. Okay, so let's say the process file, process 1 to 2 on, we will see how it will be presented on PV diagram, it is shown, and how it should be represented on TS diagram. Okay, so if we talk about process 1 to 2 process on PV diagram, it is constant volume process. Okay, so on the TS diagram it would be a curve. Okay, so this is our constant volume, and slope it will be a higher slope than of constant pressure. Okay, now if we talk about 2 to 3, this is a constant pressure process, and we will have our like it will also a curve, P is equal to constant, but the slope will be less than that of our on constant volume curve. Okay, if we talk about 3 to 4, this is again constant volume, so we will get the same process. 4 to 1 is constant pressure, we will get the same. So we have two like all fours will be curve, 2 will be constant pressure and 2 will be constant volume. Okay, so only this diagram here in TS diagram represent all the curves, all the processes in curve. Okay, any other curve have some straight lines, so this B should be the correct option. Okay, next if we go to next question, question number 30. It is given that four figures have drawn represent the hypothetical thermodynamic cycle on PV diagram and TS plane. Okay, according to first law of thermodynamics, equal areas enclosed by figure. So this is our clockwise, this is also clockwise, this is anti-clockwise, and this is also anti-clockwise. So figure 1 and 2, according to first law of thermodynamics, equal areas are enclosed by figure 1 and 2. Okay. And further, figure 3 and 4 also have a equal area, because we know that the area under the curve, like area of the in the cycle, enclosed by cycle in PV diagram or TS diagram, both will give us like like a cyclic integration of net Q or net heat. Okay, net heat or net work done, and both should be mathematically okay. Oh, sorry, equal. Okay. Next, moving to next question number 31. It is mentioned that a system of 100 kg mass undergoes a process in which its specific entropy increases, okay, from zero point 0.3 to zero point 0.4. At the same time, the entropy of the surrounding decreases from this to this. The process is okay. So for this, we can like first calculate the delta S of universe. Okay, delta of universe is equal to delta S of system plus delta S of surrounding. Okay, for delta S of system, it is mentioned that entropy is increased from zero point 0.3 to zero point 0.4, so zero point 0.4 minus 0.3 plus delta surrounding. It is mentioned that it decreased to 75 from 80. So from this we get 0.1 minus 5, and this will be equal to minus 4.9. So this value, we can say here that it is sorry for the error. So here it is given 100 kg mass, so we will multiply this by 100. So this term is in kilojoule per kg Kelvin, and this is in kilojoule Kelvin. Okay, so we will get this term to be equal to 10, and we will get value of 5. Okay, so this value is greater than that of 0, so the process is irreversible. Okay, if it was equal to 0, then the process will be reversible. Moving to next question, question number 32. So this question number 32, it is mentioned for a steady process, the condition at a stage 1 and stage 2 are respectively H1 is equal to this, S2, S1, S2. The availability at an ambient temperature of 300 Kelvin. So this is from here we will start the question of Exergy. Okay. So it is mentioned that the value of H and S are given. Okay. So we know that our Exergy function phi is defined by H minus T naught S. Okay, so the availability phi 1 minus phi 2 can be given as H1 minus H2 into, sorry, minus T naught times of S1 minus S2. So we will substitute all the values here. So 300 minus 150 is equal to 150 minus, now T naught value is 300 into S1 minus S2, 1.25 minus 0.8 will be 0.45. Okay, so we get the value equal to 15 kilojoule per kg. Okay, so option A is the correct option. Now if we move to question number 33, it is mentioned that entropy change, both like entropy change for a reversible adiabatic process is 0. It is given that in the statement A, it is mentioned that entropy change for a reversible adiabatic process is equal to 0. This is absolutely correct. Okay, of a reversible process is 0. Reasoning, it is given that there is no heat transfer in the adiabatic process. This answer is also correct. In Q adiabatic is equal to 0. Okay, and we can say that since it is a adiabatic process, so we can say that the reason is correct. Okay, explanation for the assertion. Okay, so both A and A are individually correct, and R is correct option, correct explanation